Hello and welcome back to General Biology. In this lecture, lecture 7.1, we're going to be talking about metabolism and energy change, which is going to set us up for a lot of great content in lectures 8 and 9 when we talk about cell respiration and photosynthesis. Now, before we get to that way later content, and before we even get to the lecture content for lecture 7.1, let's quickly go over lecture question 6.2. So which of the following are true regarding cell transport? If you said B, you'd be correct. Great. Nicely done. Oh, also before we move on to lecture 7.1, I kind of got lazy with my bios form during the last lecture, lecture 6.2. So I went ahead and filled it out. You can see it right below me here. That shouldn't matter though, because you guys are totally pros at bios forms by this point. Right? Right? Yeah, okay. Anyway, so there's the one from lecture 6. That's fine. I'm just going to scroll on down here so we can get started on the lecture 7 outline. There we go. Okay. Speaking of, on to lecture 7.1. Metabolism and energy change. Okay, so first off, what is metabolism? Well, there's the definition right there. You could define it as the sum of all the chemical reactions of an organism that utilizes to maintain homeostasis. There you go. It's pretty straightforward, right? So this is actually excellent example of an emergent property of life, right? So any single one of these reactions by themselves isn't, necessarily lead to metabolism. But when you put all of these reactions together, okay, now we're starting to see metabolism, this property of life, right? Cool. Now we're talking about all types of different reactions. We're talking about the ones involved with breaking down macromolecules like cellular respiration. We're talking about ones that are building macromolecules like photosynthesis. And we're also talking about things like DNA replication and production of enzymes. Well, I guess it's kind of building macromolecules, but you get the idea, right? So all the different processes together add up to metabolism. Now, metabolic pathways are kind of these particular routes or a series of reactions that occur that end with your kind of final product. Let's kind of look at this a little more specifically here. So a metabolic pathway starts with specific parts or molecules that undergo specific reactions or processes that are often catalyzed by specific enzymes. Now these processes or reactions end up with specific products. Now these products are then the kind of starting part for the next reaction in this series. Wait a second. Parts, process, products. What does that sound familiar? Anywho, now a metabolic pathway often involves kind of multiple steps or multiple reactions along the way until you finally end up with your end product like you would see here. So again, we'll use photosynthesis as a great example. You don't just have like one reaction that, boom, you have yourself a glucose molecule. There are a number of steps along the way that you have to undergo until you can finally have that end product that you see when you look at a chemical reaction of like glucose formation. Now, there are kind of two broad types of pathways. Catabolic pathways that cut or break down complex molecules into simpler molecules. Now, catabolic reactions also release energy. Cellular respiration is a pretty good example of that exact process, and we're going to go into it during lecture 9. Now, Anabolic pathways are the opposite of that. You're actually building complex molecules from simpler molecules, and you need energy to do this. Now, one example we're actually already pretty familiar with, which is the synthesis of proteins from amino acids via dehydration synthesis. Now, catabolic pathways release energy and anabolic pathways use energy, but what is energy? We'll get to that in a second. Oh, I should explain the cat GIF. I didn't just include a cat GIF or GIF because they're great. I included it because catabolic and cats, they both tend to break things, right? So this is a cat pushing a shot glass? A glass off of a table and breaking it. Both catabolic reactions and cats break things. Help you remember it. Okay. You can think of maybe anabolic adds things together. Maybe that's something, I don't know. Okay, so what is energy? Broadly speaking, energy is the capacity to do work or cause change. For example, grass utilizes the energy from the sun to grow taller. Cows then come along and consume that grass and convert the energy in that grass into milk, for example, that they would normally feed to their young. We come by and take that milk and consume it for our needs, like maybe running away from that now possibly angry cow. Okay, so there's lots of different kinds of energy, though, and let's talk a little bit more about this. For example, there is kinetic energy, or the energy of motion. Like this person diving here. They have a lot of kinetic energy as they're transitioning from the top of the board to the bottom, into the water, right? And they still actually have some potential energy as they're descending. Now, potential energy is the energy that's available to be used. For example, the person here at the top of the diving board has very high potential energy in that they have a lot of potential for movement by leaping off the board. And the person in the water, on the other hand, down here, they have no or very low potential energy because they're down in the water, right? They don't have that potential for jumping. So they need to actually do work or invest energy to restore them into a high energy state. Now, there are also other forms of energy, such as chemical energy. Chemical energy is the potential energy that's stored between chemical bonds. For example, gasoline is made up of lots of energy stored in hydrocarbons that get utilized to move vehicles via combustion engines, right? In other words, cars utilize gasoline by converting the stored chemical energy into kinetic energy to move. Now, I feel like we're talking a lot about energy, so we should probably start with some ground rules about what energy is and how converting energy actually works. So, we're going to have to dabble into physics and thermodynamics here to get a better understanding of what's happening with energy in biology. Now, thermodynamics, appropriately, is the study of energy transformations. Pretty applicable here, right? The first law of thermodynamics, you guys remember laws back from lecture 2 in the scientific method? Anyway, well, the first law states that energy cannot be created or destroyed, only converted. For example, this bear here is eating a fish. Crudely put, converting that fish energy into bear energy. A little more accurately put, it's acquiring the chemical energy stored in the fish. So what does it do with that energy? Well, each time the energy is transferred or transformed, entropy is increased. So entropy is a measure of disorder or inefficiency in a system. For example, this bear is converting the chemical energy from the fish the chemical energy from the fish, right? I said that right. Okay, good. Into kinetic energy by running. But not all of that chemical energy that it acquired was completely converted into kinetic energy. Some is actually lost as heat through the various chemical reactions that need to occur to convert that, right? This is actually the second law of thermodynamics here. More or less, entropy, okay? So let's expand that concept to a whole ecosystem. And it actually still works. So most ecosystems get their initial energy from sunlight. This energy is transformed into chemical energy through the process of photosynthesis that we'll talk about in a bit. That stored chemical energy then can get utilized for all kinds of different processes like cellular respiration, which converts that chemical energy into a more usable form in the structure of ATP. However, each of these steps in this process loses some heat. So every time you convert light energy into chemical energy, so heat gets produced. Every time you convert these organic molecules into ATP, some heat gets lost, and so on and so forth. So while the total energy in the system is constant over time, the amount of energy available to do work will decrease as some of it gets wasted as heat, right? So if we include heat in our kind of measure of how much energy is in the system, the total energy won't go down, but the amount of energy to do work will go down because now it's heat and you can't really do anything with that. Okay. So talking about total energy in a system can be pretty difficult to do and maybe not necessarily so useful. Instead, what we often talk about is how much free energy, also known as Gibbs free energy, is available. Free energy is what is available to actually do work. It can be pretty difficult to measure how much free energy exists at kind of any given moment, but what we can see is how free energy changes during a reaction. In other words, the delta G, or the change in G of a reaction. So let's take a look at this reaction here. First off, does anyone know what this reaction is? You have a glucose and some oxygen results in carbon dioxide and water and energy. Yeah, so it's cellular respiration, okay? Where a molecule of glucose with 6 carbons is plus some oxygen is broken down, torn apart, and eventually turned into carbon dioxide, 6 of them, 6 carbons, as well as water and an easily accessible form of energy, ATP. Now, when delta G, so the change in free energy, is negative or less than 0, that's when energy is released from a reaction, like during catabolic reactions. Cellular respiration, for example, is a catabolic reaction where you take a glucose molecule and some oxygen, and then you break down that glucose into carbon dioxide gas, water, and energy in the form of ATP. Now, if we're defining it as how much energy is in the system, I like to think of it as how much energy is in the molecules we're considering. For example, there's now a lot less energy in the carbon dioxide and water than there was in the original glucose, because that glucose has been converted, or the energy has been functionally converted into ATP. Now, when delta G is greater than 0, or positive, energy has been added to the system to cause the reaction, and the products have more potential energy than the reactants. Photosynthesis, for example, is an anabolic reaction that utilizes carbon dioxide gas and water to store sunlight energy as glucose. So when delta G is positive, products of the reaction have more energy stored in them. So how do we store energy? By making bonds. So a bar graph, or excuse me, a graph in general like this one here, figure 6.9, is a pretty helpful way to kind of look at this change in energy, or delta G, and how it relates to the reactants and the products. For example, in exergonic reactions, there's a lot of free energy held within the reactants. And these reactions can happen spontaneously, meaning they don't necessarily need an energy input to start them. The products then have significantly less energy stored than the reactants. Conversely, endergonic reactions have a lot more energy in the products than the reactants. But you need energy input into the system before the reactions can occur. Okay, so finally, let's kind of talk about ATP, which I've been mentioning for quite a few lectures now, and we actually haven't really talked about all that much. So ATP, or adenosine triphosphate, is what we primarily use to carry energy around, or I should say what cells primarily use to carry energy around. So why do we use this structure? Well, this 3-phosphate group at the end here is exceptionally unstable. It's kind of like a spring that you wound up really tightly. So it's very easy to attach and detach this last phosphate group. Now, if you look at the structure, can you guess why this particular bond here at the end, why is that so unstable? What about this structure would make this unstable, do you think? Right, it's because how incredibly electronegative all these oxygens are here. So you have electronegative oxygens all the way down the line. It's going to create a very unstable bond. Okay. So how do we actually carry that energy and deliver it to places then? Well, we use coupled reactions. So you pair an exergonic reaction that is providing the energy and an endergonic reaction that's using the energy. So the hydrolysis of ATP is an exergonic reaction. Water comes in, knocks and cuts off that third phosphate and releases that energy, changing adenosine triphosphate into adenosine diphosphate. So this is pretty easily done because of that very unstable third phosphate here. So you end up with an inorganic phosphate that's kind of floating around, as well as the adenosine diphosphate with 2 phosphates instead of 3, and also some energy. So what do we do with that energy, do you think? We drive an endergonic reaction. The endergonic part is called phosphorylation, where we take that phosphate that gets passed off to the reactant. So the reactant becomes a phosphorylated intermediate, and utilizes that unstable bond with the added phosphate group to kind of do work. For example, like the pump here, the sodium potassium pump, where it moves solute through a transport protein. Okay? To see how ATP functions, let's use the example of combining glutamic acid and ammonia to form glutamine, as well as some leftover ADP and inorganic phosphate, of course. So combining glutamic acid and ammonia by themselves to create glutamine is endergonic, which means it has a positive delta G. As such, this reaction won't really happen by itself. Instead, we can throw in some ATP, which will end up shedding a phosphate and sticking it onto the glutamic acid, making it this phosphorylated intermediate. Now, this phosphorylated intermediate is very unstable, though, so that phosphate will actually break, and the energy from that will enable the ammonia to replace the phosphate and form a covalent bond with the glutamic acid to form glutamine. Cool. Oh, yeah. Okay, so let's break this down a little bit further. So adding the ammonia to glutamic acid as a positive delta G, while breaking the ATP into ADP and inorganic phosphate has a negative delta G. So if we do some math here, both of the coupled reactions together, we find that this whole reaction is actually negative delta G. So it can actually be done. Great. Wonderful. Okay. So next lecture, we're going to be talking about enzymes as well as redox reactions and what those mean. In the meantime, though, what I can do is fill out my BIOS form for this past lecture since I've been so lazy about it. There we go. That's nice and filled out. But you guys could have already done that. I'm sure you did it already while you're taking notes. You're old hats at this. Anyway, so enzymes, like how they function and the things that make them function better or worse. We're also going to talk about redox reactions and what electron acceptors are, which are going to be really important when we get to photosynthesis and cellular respiration. Now, before we get to lecture 7.2, let's move on to lecture question 7.1. Which of the following are true regarding endergonic and exergonic reactions? Go ahead and read through that question, and I'll see you in lecture 7.2. Cool.